This is our poster about basic counting techniques and probability. And the first part is counting techniques belongs to Boran.
Yes, so counting techniques is my part. For introduction, this topic will cover counting or enumerating various arrangements of discrete objects with predetermined constraints such as sets, sequences, functions, and so on. Mathematical and computer science both heavily utilize counting, for instance, determining of complexity of algorithms, computing discrete probability of some events. So we have two rules here. First rule is the sum rule. If there are n A ways to do A, and unlike them, there are n B ways to do B, then the number of ways to do A or B is NA plus NB. The second rule is product rule, and if there are n A ways to do A and n B ways to do B, then the number of ways to do A and B is NA times NB. This is true if the number of ways of doing A and B is independent. No matter what choices you make for A, B has the same number of choices. And inclusion-exclusion principle. A intersection B equals to A plus B minus A combination B. And also we can use this principle three sets of integers too. And pigeonhole principle. If k plus 1 objects are placed into k boxes for any k in natural numbers, at least one box contains more than one object. For example, at least two students got this exam will receive exactly the same final exam mark. Why? That's because there are at least 102 students getting this exam, so at least 102 objects. Final exam marks are between 0 to 100, so exactly 101 boxes. And permutation and combination, first part, permutation, is each of the various alternative arrangements or orders that set or number of items may take. For example, how many permutations are there of 6 things taken 3 at a time? Answer is 6 choices for the first thing, 5 for the second, and 4 for the third. The answer is 120. Combination is selection of things from a group of unique items where the order of the selection is irrelevant. Example, how many ways are there of choosing 3 things from 6? Answer is, since order doesn't matter, answer is 20. The binomial theorem. As the power increases, the expansion becomes lengthy and tedious to calculate. A binomial expression that has been raised to a very large power can be easily calculated with the help of the binomial theorem. And the Pascal identity is a theorem of combinatorics dealing with combinations. It can be used to simplify complicated expressions involving binomial coefficients. And Pascal's triangle is a triangular array of the binomial coefficients that arises in probability theory, combinatorics, and algebra. The rows of Pascal's triangle are conventionally enumerated starting with the row n equals 0 at the top. The entries in each row are numbered from the left beginning with k equals to 0 and are usually staggered relative to numbers in the adjacent rows. And that's all I can say about
Well,
my part of
thank
the
you,
poster.
Boran, for a clear explanation. And the second part, the probability is my part. Well, the probability theory firstly invented for better understanding the gambling games. But in the present times, we are using that theory in in many disciplines like study of social sciences, genetics, algorithms, psychology, and industrial efficiency. For example, for determining a better way of production, we are getting help from that theory. Then the finite probability, which also known as discrete probability, it means when the sample space is a countable number, uh, we we name this type of probabilities as finite probability or discrete probability. And there are three keywords for this probability. Also, these keywords are uh, using in the other probability types too. They are so basic things: experiment, sample space, and event. So an experiment is process that gives outcomes to analyze and study probabilities associated with different events. And the sample space means uh, that is the uh, sample space of the experiment is a set of possible outcomes. And event is a subset of sample space. So in the below in the white place you see the Laplace's definition of the probability. And in the right side you see the a picture of Laplace. And Laplace was a mathematician who has very important uh, very important parts in probability. Uh, and the complementation of an event in a dice rolling experiment, if you calculate the probability of getting one, you can calculate the getting any number except one by using that theorem. So you see in the picture there is a sample space and an event A, and uh, in this diagram, inside of the circle is representing the probability of this event A, and outside is uh, representing probability of complementation of A. So we are assuming that probability of this sample space is one, and if you subtract if you subtract that event A from the probability of event A from the one, you will get the probability of complementation of A. And the onion of these any two events, uh, we are using the equation you see in the rectangular. Uh, when we need to calculate probability of any two events, first we are adding their probabilities. Like let's say you have event A and event B, you are adding their probabilities, and then you are subtracting intersection of these events, because as you can see in the picture, when you add these probabilities, actually you are counting these intersection parts twice, so you are just subtracting one of them and you are getting the probability of onion A and B. And there is a conditional probability thing. We use this when we have a knowledge about an experiment before it's happened. Uh, you can think about that with uh, with an example. Let's say uh, you are rolling three six-sided fair dice, and you already know what will the first die first dice output. In in this case, you are using conditional probability, and you can see the equation in the rectangular. And the bias theorem is so we use this bias theorem in some special cases, like let's say you know probability of E given F, but you want to find probability of F given E. In these cases, we are using bias theorem. Uh, the bias theorem is very helpful in our calculations. And the expected value is uh, it is represents weighted average of the random variables values. The expected value of a random variable can be calculated by adding up the probabilities of each element in the sample space multiplied by the corresponding value of the random variable. So let's say we are rolling again a six-sided fair die, and uh, there are six possible outputs that you can 1 to 6, and each output has 1/6 probability, and if you multiply this probability with each of these outputs, and uh, if you sum them, you'll get 3.5, which will be your expectation uh, about that experiment. And also, you can think the expected value as the mean value of an array. And in the variance part, so the variance is about how much the values of a random variable deviated from their average. Uh, you see two example in the below. There are two different integer arrays. Uh, One of them is S, and it has 1, 2, 3, 4, 5 inside. And there is an X event. It says choosing any number. So the probability of this X is 1/5 for this sample space. And you see the expected value for that array is 3. And also in the right side, array A, also it has 3 as expected value, but as we can see, they have different arrays. So in these cases, we are using variance to evaluate the arrays. You can see in the left part variance is 2.5, and in the right part variance is 4. The variance is higher in the right part because the difference between the numbers inside of the array are bigger, but in the left side it is lower, so the variance is lower. And that's it. Thank you for listening.